Our next speaker is Roger Sayle with NextMove software. I'll be talking about efficient simulus matching of multiple smarts using the ChemAxon toolkits.
First of all, I'd like to thank Alex and the ChemAxon folks for allowing me the opportunity to speak here. We're greatly enjoying the conference. I hope you are too. One of the things that's a bit difficult about this type of conference compared to ones I've gone through is the broad diversity of people here. We have IT people, scientists, developers, or what have you. And so I hope when I was shuffling the slides today, I have a bit of something for everyone. Essentially, the problem I'm looking into or considering today is the problem of doing, matching multiple smarts or substructure patterns, at the same time. It turns out that, a frequent use of pattern matching or cheminformatics tools is to try and recognize features or substructures of a molecule, and the different methods and paradigms of doing that. A quick overview of the talk is to talk a teeny bit about, chemical pattern matching, a teeny bit about, the problem or efficiently how you match a single pattern against a molecule, extend that to matching, multiple patterns at the same time. The approach that I propose or discuss is, toolkit code generation, so generating ChemAxon Java code that calls the ChemAxon APIs, and then finally some performance figures and conclusions. That, as I said, I shuffled all the slides together so the flow might not follow, exactly the plan, as described there. So it turns out I've been, wondering and working on the problem of pattern matching in cheminformatics for a good number of years. So these are a number of papers from nearly 15 years ago on the problems of how one officially does, pattern matching. Is that the Daylight meeting in 1996, I described, how one recognizes that, for example, a connection table contains a cyclic peptide. Can I find all of the pentacyclic, peptides in a registry system? Or if I read from a SMYBYL string, can I generate the PDB file, naming atoms and histidines and residues? And then in 1997, at the Daylight mug meeting, was the problem of how one canonicalizes SMARTS patterns, how one says that one pattern is a subpart of another, or that two SMARTS patterns are equivalent. And so this is a sort of, a decade later, what type of problems can we tackle and move on and try? So chemical pattern matching is one of these, difficult, tricky technical problems of subgraph isomorphism. The job is to try and identify a subfeature of a molecule. Query patterns are typically specified as SMARTS, MDL query files, ChemDraw files, or Marvin queries. And algorithms to do them have traditionally fallen into two major classes: Ullman's isomorphism algorithm or McGregor's backtracking search, that are essentially the two underlying sort of principal ways of tackling the problem. But of course, those are the ways that it's best to match a single pattern against a single molecule. If one thinks about how, JCHEM does searches of databases, that if you have a single pattern that you want to run across a database of molecules, it turns out that, brute forcing you to do one smart match at a time is not the most efficient way of doing it. The advantages of having fingerprints and doing fingerprint pre-screens, triage-like analysis, atom frequency counts, allow you to dramatically reduce the number of comparisons you do when you do a search. The thing that I'm talking about today is essentially the contrapositive of that. The other analogy is to say, well, I have one molecule and a huge number of SMARTS patterns to match against it. Is there a better way of pre-processing those patterns or rearranging them to make the matching more efficient than saying, does pattern 1 match, does pattern 2 match, does pattern 3 match? Essentially, the problem is, almost an academic one unless you're doing multiple SMARTS matching. It turns out in the vast majority of the toolkits or lots of applications, whenever you're matching just a single pattern, it turns out to be file I/O time, or essentially processing of molecules, that ends up being the predominant and the running factor. And so a simple application like a mol grep that runs through a database and counts the number of times a particular substructure occurs is dominated by the I/O time, the ring perception, and reading things in. It turns out the different toolkits then are spending varying amounts of time. The actual SMARTS matching time in these applications is very small compared to how things go. One of the reasons we're all here today is that ChemAxon has very, very good and very, very efficient implementations. CDK, for example, did not finish is not quite true. It stopped after 4 seconds and said the first tin it encountered decided to stop and call exit. One of the problems we have in our field is having robust tools that allow us to work on very large databases. And unfortunately, some of the public domain tools are not as robust as the commercially provided ones. So in the world of cheminformatics, there are a number of applications where you match multiple SMARTS at the same time that are phenomenally used in common workflows in the pharmaceutical industry. Compound filtering, where you're looking for interesting drug-like molecules or sets of reagents that you want to use in a reaction. Fingerprint generation, such as max keys or particular ways of, fragment or substructure based keys. And then also, for example, in computational chemistry and modeling, atom typing, how one prepares molecules for force fields and doing minimization approaches. And so I'll talk about a little about each of these applications and methods of improving things. But to introduce the problem of, or the method I'm proposing to solve this class of problem, we'll consider an interesting class of, useful filter to use in a cheminformatics application. The question that one says is like, well, are the compounds I'm ordering from this reagent radioactive or not? Clearly the health and safety people, would like to know that if things are decaying on them, that's going to cause a problem. A molecule is radioactive if any of its atoms are radioactive. An atom is radioactive if it's not stable. It turns out there are 255 known stable nucleotides, and so therefore if your molecule doesn't one of those or uses an element that has no stable nucleotides, it is by definition a radioactive compound. And so it turns out this is then hydrogens from all the elements from hydrogen to lead, with the exceptions of technetium and promethium. And so an interesting SMARTS pattern for is stable is to say, well, a hydrogen without any isotope specified, protium or deuterium, tritium being radioactive is not on the list, or a helium without an isotope specified, and you end up with a big list like that. As I mentioned previously in my work on SMARTS, there's a marvelous way of inverting the logic of that says is radioactive is the not of that SMARTS, which ends up being written like this. I hope you can read at the back, but of course the result is a marvelous SMARTS pattern that is almost like a pathological worst case for typical SMARTS matching algorithms. And of course, if you then feed this into the ChemAxon toolkit and ask it to zip through a file, just doing a simple match to say, does it have a specified isotope? Only takes 6 seconds to match. If you give it the large radioactive SMARTS pattern we said, is the processing or traversing of that SMARTS query for each atom, creates a large overhead and therefore takes significantly longer to do processing. But of course, the approach or the solution to this problem is what in computer science is the difference between interpreters and compilers. Most SMARTS matches are implemented as interpreters. So in ChemAxon at runtime, the SMARTS is read in, a data structure is constructed in memory, and that is traversed multiple times in order to do the match. And this is identical or analogous to the way that Perl and Python act as scripting languages in computer science. It turns out for static patterns or substructures that don't change very often, you can compile them in advance. It effectively says, well, here is the code that I would write in order to do that match. Analogous to the way that C or Fortran is executed. Essentially, you generate the Java code way ahead of time and match over that. So essentially, you can read in the SMARTS pattern that we just saw and automatically transform it into a Java class or method called isRadioactive. You pass in a molecule that zips over all of the atoms and does the switch on the atomic number and then switch on the mass number. And as if by magic, you then just link that into the same program. And of course, it runs in almost exactly the same time as doing the file I/O. That basically says if you know in advance the patterns you want to do, you can generate the ChemAxon Java, and of course, in some cases, get 700 times speed ups for these types of things. It's also an interesting way of avoiding vendor lock-in or transitioning from one data structure to another. We heard talks earlier in the week about large investments made in Daylight that they're now shifting to ChemAxon tools. It turns out this higher level view of generating code allows you to have backends or read the same SMARTS patterns and generate ChemAxon code, OpenBabel code, RDKit, Pipeline Pilot, Central, and so on. So to give an example, here is exactly the same function generated for C++ using OECHEM. One of the advantages of this processing or compilation step is the number of optimizations and transformations that can go underneath the surface. It turns out the resulting code, when it's doing all sorts of interesting backtracking and matching, can make advantage of the types of chemistries going on. A good benchmark for match iteration performance is to compare the isomorphisms of ferrocene to itself. So given a SMILE string such as this, you say, well, when I match it against myself, how many ways are there of doing it? And of course, there are 200 different isomorphisms matching ferrocene to itself. And that, asking the SMARTS matcher in OECHEM to do this takes 3.5 seconds to find all 200 isomorphisms. The interesting thing is that if you compile the pattern in advance and generate, these C++ calls. So using the same OECHEM library and doing the same things, you can complete, again, hundreds of times faster. Likewise, one of the advantages of automatic code generation is that the ability to produce, lazy iterators over molecules when you're doing pattern matching. Most cheminformatics toolkits provide a mechanism for training a set of matches given a query pattern against a target. But many of these implementations, and I'm sure to say that ChemAxon is one of the nice exceptions that has a nice lazy implementation, are eager, and so you determine all of the matches or patterns in advance. And so the lazy implementations, ones that say, well, what are the first 4 matches or what are the first 3 matches, are more efficient ways of producing those, and we'll get back to that a bit later in the talk. Another example of the types of applications that do pattern matching are to say it's like atom typing. So when you write out mol2 files or convert from SMIL strings to SYBYL input format, you end up with large sets of atom types that say, aromatic nitrogen, sp3 carbon, sp2 carbons, and atom type files. Here's another example of where a fairly static set of patterns is used again and again, and used, for example, in molconvert for generating TRIPOS SMILS files. One of the things that got me interested in this, a long time back, was when I was working at OpenEye on the LEXICHEM, name to structure and structure to name programs, is that you end up with internally a very large list of 1,034 atom types for determining the principal suffix in an IUPAC name. So the way that you name a compound is based on the most senior functional group in there. And so you end up with a pattern like this for carboxylate, carboxylic acid ester, amide, hydrazide, aldehyde. And so the traditional way of implementing this would be to ask for each of the 1,034, meaning patterns, where in the molecule does that match? And the next one, where in that molecule does that match? It turns out there's a very clever way, of applying or spotting those patterns far more efficiently than doing things sequentially, that goes all the way back to the 1970s and the work of chemical abstracts. That essentially, works by iterated passes over the molecule. In the first pass, each vertex is assigned a particular atom type based purely on itself, ignoring its neighbors. And in subsequent passes, you consider the neighbors of each atom type to itself. So it's very similar to radial ECFP fingerprints. One can imagine then that the way in LEXICHEM in the first pass, carbons of degree 3, so sp2 carbons, terminal oxygens, and nitrogens, are initially being typed. In the second pass, every nitrogen that's connected to another nitrogen becomes a hydrazine. Every sp2 carbon that has a keto oxygen next to it becomes a carbonyl. If it has one of those, carboxylate. And so essentially by a number of repeated iterations, amides can become hydrazides, hydrazines, what have you. And it turns out all 1,034 atom types are assigned in 4 passes. So essentially 4 scans over the molecule, you've managed to match all 1,034 patterns. One of the other interesting applications or types of this type of pattern matching is in the assignment of MDL, now Accelerus, max 166-bit keys. So a common use or standard benchmark when doing chemical similarity is to compare how well the fingerprints compare. And so there are a public set of 166 SMARTS patterns that are commonly used or provided by OpenBabel, RDKit, and CDKit. An excellent discussion on this was provided by Andrew Dalkey available online, where you have the large number of patterns that you use to it. It turns out there are 150 regular patterns, 8 atom pattern counts, and 6 complex pattern counts. It turns out that when you process and go through them, relationships between patterns can be non-obvious. So in the RDKit provided SMARTS, the pattern for heterocycle is this pattern. Bit 120, which is more than one heterocyclic atom, is that. And of course, very few people, or essentially without processing, should think that those two are identical. It's not trivial. Counting semantics can be unusual. Here, for example, when you have an oxygen with a non-ring bond to an atom that then has a ring bond from it, by its very default, must match more than once. Imagine a phenolic oxygen going to a ring carbon atom. There will always be 2 neighbors in the ring, and so the number of matches is going to be always greater than 1. The real question is whether greater 2 or greater. And likewise, a number of complex patterns, such as this star-based thing of can I find a substructure that has 4 atoms in a configuration, can be mapped into a single predicate over a single atom. Do I have 4 or more connections? It turns out then when you start staring at these patterns in advance, or the computer can look at them, it can realize that a large number of bits in these fingerprints are set purely on what the atomic number is, that essentially you can go through and analyze those. Likewise, a bit 134 of being a halogen, you can tell this from this set. So essentially with a single scan over a molecule, you can switch or look at each atomic number, end up setting a large fraction of the bits in the fingerprint very efficiently. Likewise, some issues on counting and non-counting. One of the nice things is you all have this online, and so it's great to look at it. The end result is that the program that takes this in and reads it out generates a fingerprint class derived from ChemAxon's MD generator class that then provides the generate function that goes through, sets the fingerprint, and all the code is inserted here to then do the SMARTS match. It turns out there are a few exceptional bits that have to be handled in different ways. So you manually insert that bit 125 is found by finding more than one aromatic ring. But the nice thing is that the generated code is then a single function that can be applied and used within the ChemAxon code that rather than, runs much faster than standard implementation. One of the things I've done is recently provided this implementation and sent it to the forum today. So the original implementation is based on the Miklosh's original implementation that was on the help page or forum. It turns out the number of optimizations then reduces the runtime. And so folks in the audience can now do max-based fingerprinting phenomenally quickly. But of course, performance isn't everything. It's very nice to be able to get max-like fingerprints very quickly. But of course, my motivation and rationale for doing this is to tackle the problems that people haven't done in the past. A good example is the use of Thomson Reuters CPI codes. It turns out, well, if you can handle very small fingerprints efficiently, perhaps we can work on much bigger sets of fingerprints. Effectively, the way that the World Patent Index analyzes or indexes its database is to assign 1,080 substructure fingerprints to each molecule. Those people who are used to using SDN Express will realize that molecules like ranitidine end up having all of these bits set manually. Bit M211 is a methane or methyl group. Bit H183 is two amino acids bonded to a C atom aliphatic group. You end up with a huge number of interesting bits. But of course, this is then the standard way that the commercial companies index their patent data. But again, coming one step closer, one of the things that's most interesting to me is in the problem of chemical text mining and the representation of structures you pull out. A classic example of a patent bust is the 2009 biopatent of vardenafil, the classic nitrogen switch, in which the title of the patent was 2-phenyl-substituted imidazole-triazonones as phosphodiesterase inhibitors. And the question that I ask is, how much information could be mined from the title alone? It turns out that name-to-structure programs can find nothing more than the phenyl in the title. It turns out that although there's a lot of information in the word imidazole-triazonones, it is not a single connection table. It represents a single molecule, but describes chemically a large class of molecules. The phrase 2-phenyl-substituted triazonones is the two substituted phenyl of imidazole-triazonone. Imidazole-triazonone is a ketone or keto suffix of imidazole-triazine, and it turns out that imidazole-triazine is imidazole plugged into a triazine, of which there may be three different classes. So it turns out there are 14 imidazole-triazonones and 54 imidazole-triazonones. If one was to ask yourself, well, can I get that structure or that set of SMARTS out of a patent to say to look for it? How would I then search an internal registry system to say, well, how many examples of those do I have? What ones can I get from compound manufacturers? And so it turns out that these methods of generating SMARTS matches can provide very efficient implementations whereby, without ever going via a single connection table, you can turn the name directly into the SMARTS pattern matcher, whereby this is essentially the state machine that would go through and match all of those things. So in the end, I'd just like to say that compilation of SMARTS patterns is shown to improve the runtime performance of subgraph matching. The biggest gains are seen when matching multiple patterns or large numbers of them, and the increasing speed improvements allows expressive power and previously impossible or prohibitive queries to be tackled. I should skip over mentioning. I'd like to thank you for your time and Alex for inviting me. Vertex, who initially expressed an interest in providing this sort of thing, and thank you for your questions.
Thank you very much. Do we have some questions?
Roger, that's a fantastic talk, but your last set of comments about the nitrogen switch there implies a name to SMARTS and SMARTS to name utility. What are your thoughts on that?
I think that's the direction in which this is going. Is my predominant interest in doing this sort of thing is that there are a number of things we're used to names like halo-substituted alkyl benzoic acid. The thing is that connection tables or simple name-to-structure programs, the ChemAxon name-to-structure or ops in Cambridge Soft, just don't handle those types of generic classes of compounds. And that I think that, yes, skipping out the connection table and doing straight to SMARTS is perhaps the way forward to go.
So you found speedups of from, I think, 8 to 400 or something like that. So all of them are very impressive. But so naively, I would expect that the benefit you get from interpreting to compiling would be more or less constant. Is that true, or did you analyze why there is such a wide range of speedups?
It's the different sets of optimizations that get applied. The 8 times speed up at the end was essentially, all of the pattern matching is still being done in the ChemAxon toolkit rather than, it's an O1 or an O2 versus an O3 as a compilation option, is that it's possible to compile those pattern matches down all the way to those things. Likewise, given a set of patterns that you're matching, the amount of redundancy or overlap there are between them. If you end up with a large number of very disjoint or unrelated sets of patterns to match, that almost the best you can do is get a linear speed up. It turns out for things like imidazotriazonones or matching steroids, that there turns out to be far more common structures and substructures that you get to be able to reuse the results from. So